You probably think your body is solid. You can press your hand against a table. You can sit in a chair. You can feel the floor pushing up on your feet. Everything about your daily experience tells you that matter is solid, compact, and filled with substance. But physics tells a very different story. In fact, if you removed all the empty space from the atoms in your body, the entire mass of you would shrink to something smaller than a grain of sand. Not a pebble, not a marble, a grain of sand. And yet, it would still contain every atom that makes you who you are. Now that sounds absurd at first. After all, you can see your body. You can feel it. You can knock on a table and hear the solid thud. So how can something that feels completely solid actually be almost entirely empty space? Well, this is where physics begins to reveal that the world you experience is not quite the world that actually exists underneath. Our senses evolved to help us survive. They were never designed to show us the microscopic structure of reality. When you touch a table, your brain tells you that you are making contact with a solid surface. But in the language of physics, something much stranger is happening. The atoms in your hand never actually touch the atoms in the table. Not once, not ever. Instead, invisible electric forces push them apart before they can come into contact. What you experience as touch is really the resistance between electric fields. In other words, the feeling of solidity is not caused by objects being packed full of material. It is caused by forces. Invisible forces acting between particles. And once you begin to look deeper into what atoms actually are, the picture becomes even more surprising. Because an atom is not a tiny solid ball like people once imagined. It is mostly empty space. Enormous empty space compared to the tiny nucleus at its center. In fact, the empty space inside atoms is so vast that if you could somehow remove it, every human being on Earth could be compressed into something the size of a sugar cube. Now, of course, this is just a thought experiment. Nature doesn't allow you to squeeze matter like that under ordinary conditions. But the calculation itself reveals something remarkable about the structure of matter. The things we think of as solid are mostly emptiness. Now you might wonder, if that's true, why don't we fall straight through the floor? Why doesn't your hand pass right through the table? If everything is mostly empty space, why does the world feel so solid and stable? That question leads us directly into the strange rules of the microscopic world, where atoms obey laws that are very different from the physics of everyday objects. Laws involving electric forces, quantum mechanics, and something called the Pauli Exclusion Principle. These rules create the illusion of solidity that we experience every day. But underneath that illusion, matter behaves in ways that are far stranger than our intuition expects. So the next time you look at your hand, consider this. What appears to be a solid object is actually a vast structure of mostly empty space, with tiny nuclei and clouds of electrons interacting through invisible forces. And once you truly understand what atoms are, the idea of solid matter begins to look less like a fundamental property of the universe, and more like a very convincing illusion. Because when you examine reality at the deepest levels we currently understand, what you find is not hard little particles packed together. What you find is something much stranger, patterns of energy, fields interacting with other fields, probabilities instead of certainty. And this is where the real story begins. Because once you understand what atoms really are, your entire sense of reality starts to change. When you press your hand against a table, it feels obvious what is happening. Your hand is touching the table. Two solid things meet, and the contact stops your hand from moving any further. That explanation feels so natural that we rarely question it. But the strange thing is, in the language of physics, that explanation isn't actually correct. The atoms in your hand are not touching the atoms in the table, not in the way we normally imagine touching. What's really happening is something far more subtle and far more interesting. To understand this, we have to zoom down into the structure of matter itself. Everything around you, your body, the air, the chair you're sitting in, is made of atoms. Atoms are the fundamental building blocks of ordinary matter. But atoms are not solid little spheres, like tiny billiard balls. That picture is useful for some explanations, but it hides what's really going on. An atom has a very small nucleus. At its center, made of protons and neutrons, and surrounding that nucleus is a region where electrons exist. Now the important thing here is that electrons carry electric charge. In fact, electrons carry negative electric charge, and the protons in the nucleus carry positive electric charge. An electric charge creates electric forces. These forces extend through space in what physicists call electric fields. So every atom is surrounded by electric fields created by the charges of its electrons and nucleus. Now imagine bringing your hand down onto a table. As the atoms in your skin approach the atoms in the table, the electrons in both sets of atoms begin to interact. Remember, electrons all carry the same type of electric charge, negative, and charges that are the same repel each other. They push away from each other. This means that long before the atoms in your hand could ever physically overlap with the atoms in the table, their electrons begin to repel each other through their electric fields. The closer the atoms get, the stronger this repulsion becomes. Very quickly, the repulsive force becomes strong enough to stop your hand from moving further into the table. Your muscles are pushing down, but the electromagnetic forces between the atoms push back. And what you feel in your nerves, what your brain interprets as the sensation of touch, is actually the resistance created by these electromagnetic interactions. So when you press your hand against a surface, what you are really feeling is not two solid objects colliding. You are feeling electric forces pushing back against each other. In a very real sense, the atoms never actually come into direct contact. The electric fields around them prevent that from happening. This leads to a strange conclusion. You have never actually touched anything in your life. That sounds like a trick sentence, but it isn't meant as a philosophical joke. It's simply a statement about how physics describes interactions between atoms. What we call touching is really the interaction of electromagnetic forces. Your finger approaching a table, a glass sitting on a countertop, your feet pressing against the floor. All of these situations involve atoms resisting each other through electric fields. The illusion of solidity comes from the fact that these forces become extremely strong at very small distances. When atoms get very close together, the electromagnetic repulsion increases dramatically. To your senses, this feels exactly like a solid barrier. Your brain doesn't detect electric fields directly. It only detects the mechanical pressure created by those forces acting through the atoms in your nerves and skin. So your mind constructs the experience of solid matter. But the deeper reality is that matter behaves more like a network of interacting fields than a collection of tiny hard objects. Another surprising aspect of this interaction is that atoms are mostly empty space. The nucleus at the center of an atom is incredibly small compared to the overall size of the atom. The electrons are not little marbles orbiting neatly like planets around the sun. Instead, they exist in regions described by quantum mechanics, what physicists call electron clouds or probability distributions. But even before we get into those quantum details, the key idea is that atoms are not densely packed objects. They are structures with enormous empty regions inside them. Yet despite that emptiness, when billions upon billions of atoms come together to form a piece of matter, the electromagnetic forces between their electrons create a powerful resistance to compression. That resistance is what makes a table support your weight. It's what makes a wall stop you from walking through it. It's What allows a chair to hold you up when you sit down? The solidity you experience in everyday life is the macroscopic effect of countless electromagnetic interactions happening between atoms. Every time you pick up a cup, trillions of electrons in your hand interact with trillions of electrons in the cup. The forces balance in such a way that the cup stays in your grip instead of falling through your fingers. To your senses, this feels like direct contact with a solid object. But to a physicist, it looks more like an intricate dance of electric forces. And this realization begins to shift the way we think about matter. The world appears solid because our senses interpret electromagnetic resistance as solidity. But the underlying structure of matter is far more subtle. It's not packed with substance the way a rock might appear to be. Instead, it's a dynamic system of particles and fields interacting according to the laws of electromagnetism and quantum mechanics. Once you begin to see the world this way, the familiar experience of touching something starts to feel a little strange. When you press your hand against a wall, there is no moment when the atoms in your skin actually collide with the atoms in the wall. Instead, their electric fields interact and push back. Your body stops moving because the forces become too strong to overcome. The sensation of solidity is the result of those forces being transmitted through the atoms of your skin and into the nerves that signal your brain. So the next time you touch a table or hold a cup or feel the ground beneath your feet, remember that what you're experiencing is not solid matter in the way it appears. What you're really experiencing is the strength of electromagnetic forces acting between atoms. And this is only the beginning of the story. Because once we look inside a single atom, we discover that the illusion of solidity becomes even more astonishing. Inside the atom itself lies an enormous expanse of empty space far greater than most people ever imagine. Now, let's look inside an atom itself, because this is where the story becomes truly surprising. When people first learn about atoms, they often imagine something like a tiny solar system, a small nucleus in the center, with electrons orbiting around it like planets around the sun. That picture is useful as a first approximation, but it hides the most astonishing feature of atoms. Almost all of their volume is empty space. To understand just how empty an atom is, we need to think about scale. The nucleus at the center of an atom contains nearly all of the atom's mass. It is made of protons and neutrons packed together in an extremely small region. But compared to the overall size of the atom, the nucleus is unbelievably tiny. Here is a way to picture it. Imagine a large sports stadium. In the very center of the field, place a single peanut. That peanut would represent the atomic nucleus. Now where are the electrons? If the scale is accurate, the electrons would not be hovering just above the peanut. They would be somewhere near the outer seats of the stadium. And between the peanut and those outer seats, there is almost nothing. Just empty space. That comparison gives you a sense of how enormous the empty region inside an atom really is. The nucleus occupies only a tiny fraction of the total volume. Everything else is the region where electrons exist. But even that description requires a little care, because electrons are not tiny balls moving along fixed paths. Early models of the atom imagined electrons orbiting neatly around the nucleus, like miniature planets. Modern physics tells us that this picture is not quite correct. In quantum mechanics, electrons are described by something called a wave function. This wave function tells us the probability of finding the electron in a particular region of space. In other words, the electron does not have a single precise location until a measurement is made. Instead, it exists as a spread-out probability distribution. Physicists often describe this region as an electron cloud, not a cloud made of droplets, but a cloud of probabilities. In some regions of the atom, the electron is more likely to be found. In other regions, it is less likely. The shape of this cloud depends on the energy state of the electron and the quantum rules governing the atom. So when we say an atom is mostly empty space, we have to understand what that really means. It doesn't mean the atom is literally nothing inside. It means that the dense nucleus occupies only a tiny central region, while the electrons exist as diffuse quantum distributions spread across a much larger volume. The atom is more like a structure defined by fields and probabilities than a miniature solid object. And this leads to a strange realization. Everything you see around you, your body, the air, the walls of this room, is built from atoms with this same structure. Tiny nuclei surrounded by enormous regions where electrons exist as quantum clouds. When trillions upon trillions of these atoms come together, their interactions create the materials we experience as solid matter. But underneath that familiar solidity lies a vast amount of empty space. So the next time you look at your hand, remember what it is really made of. Not dense chunks of substance packed tightly together, but countless atoms, each one mostly empty space, arranged in patterns and held together by the invisible forces of nature. And once you start thinking about matter this way, the world begins to look very different. When physicists began studying atoms in detail, they quickly discovered that the rules governing the microscopic world are very different from the rules we experience in everyday life. The objects around you, a chair, a rock, a glass of water, behave in ways that seem predictable and solid. But when you look at the particles that make up those objects, the familiar picture begins to break down. This is where quantum mechanics enters the story. Quantum mechanics is the framework physicists use to describe how matter and energy behave at extremely small scales. And one of the most surprising things it tells us is that particles like electrons do not behave like tiny solid balls moving along definite paths. Instead, they behave more like waves of probability. Earlier, we talked about electron clouds surrounding the nucleus of an atom. That cloud is not a physical mist or fog. It represents the probability of finding an electron in a certain region of space if you perform a measurement. In quantum mechanics, the electron is described by a mathematical object called a wave function. The wave function spreads out through space and contains information about where the electron is likely to be detected. In some regions, the probability is high. In others, it is extremely low. But until a measurement is made, the electron does not have a single definite position the way a classical object would. This idea is deeply counterintuitive. In our everyday experience, objects always have clear locations. A ball is either here or there. A chair occupies a definite place in the room. But electrons inside atoms do not behave like that. Their behavior is governed by the principles of quantum uncertainty. One of these principles, known as the Heisenberg uncertainty principle, tells us that certain properties of particles, like position and momentum, cannot both be known with perfect precision. At the same time, this is not simply a limitation of our measuring instruments. It is a fundamental feature of how nature behaves at small scales. Because of this, the structure of matter is not built from tiny solid objects arranged like bricks. Instead, it is built from particles whose behavior is described by probabilities and wave-like patterns. The atoms in your body are not miniature solar systems made of hard little spheres. They are quantum systems where electrons exist as probability distributions around the nucleus. And when enormous numbers of these quantum systems interact, they produce the stable structures we experience as matter. So when you look at your hand and think of it as a solid object, physics suggests something more subtle is happening. What you call your body is really an organized pattern of atoms. And those atoms themselves are patterns of probabilities governed by quantum laws. In other words, the solidity of the world emerges from rules that operate at a much deeper level than our senses can perceive. The familiar reality you experience is the large-scale result of countless quantum interactions taking place every moment. At this point, a very natural question appears. If atoms are mostly empty space, and electrons exist as diffuse probability clouds, why don't you simply fall straight through the floor? After all, if your body and the floor are both made mostly of empty space, it might seem like there should be plenty of room for the atoms in your body to pass right through the atoms in the ground. But the reason this doesn't happen lies in the fundamental rules of quantum physics. Two important ideas are responsible for the stability of matter: electromagnetic repulsion and the Pauli Exclusion Principle. First, remember that electrons carry negative electric charge. When the atoms in your body approach the atoms in the floor, the electrons in both sets of atoms begin to repel each other, like charges push away from one another. As the atoms get closer, this repulsion becomes stronger and stronger. Eventually, it becomes strong enough to stop the atoms from moving any closer together. That electromagnetic resistance is one of the reasons the floor feels solid beneath your feet. But there is another rule that plays an equally important role. This rule is called the Pauli Exclusion Principle. It states that two electrons cannot occupy exactly the same quantum state at the same time. In simple terms, electrons cannot all pile into the same place with the same properties. If the atoms in your body tried to overlap with the atoms in the floor, many of their electrons would be forced into identical quantum states. The laws of quantum mechanics forbid this. As a result, the electrons rearrange themselves in ways that create an additional resistance to compression. The combined effect of electromagnetic repulsion and the Pauli Exclusion Principle prevents matter from collapsing into itself and stops objects from passing through each other. So when you stand on the floor, trillions upon trillions of electrons in your body interact with trillions of electrons in the ground. Their quantum rules and electric forces push back against each other. The universe has rules. And those rules are the reason you can sit in a chair instead of falling straight through it. Now imagine something extraordinary. Suppose you could somehow remove all the empty space inside the atoms that make up your body. Not the particles themselves, just the empty space between the nucleus and the electrons, and the empty space between atoms. What would remain? The result would be astonishing. Your entire body would shrink dramatically. All the mass that currently forms your body would compress into something incredibly smaller than a grain of sand. And yet it would still contain the same number of atoms, the same particles, and the same total mass. This idea is not meant to describe something that can actually happen under normal conditions. It is a thought experiment physicists use to understand just how much empty space exists inside matter. Because when you calculate the relative size of atomic nuclei compared to the full size of atoms, you discover that nearly all of the volume we experience as solid matter is actually empty. If you perform this compression, not just for one person, but for every human on Earth, the result would be equally surprising. All of humanity could fit into a volume roughly the size of a sugar cube. The mass would still be the same, but the empty space would be gone. Nature does produce matter with densities somewhat like this, but only under extreme conditions. One example exists in the universe: neutron stars. A neutron star forms when a massive star collapses under its own gravity after a supernova explosion. The pressure becomes so enormous that atoms are crushed together and electrons combine with protons to form neutrons. The result is matter packed together with incredible density. A single teaspoon of neutron star material would weigh billions of tons on Earth. Compared to that kind of matter, the atoms in your body are incredibly spacious structures. Vast regions of emptiness surrounding tiny, dense nuclei. And that realization once again reminds us that what appears solid in everyday life is built on a structure that is mostly empty space. When you step back and look at everything we've discussed, a strange conclusion begins to emerge. The human body feels dense and solid. You can feel your bones, your muscles, the pressure of the ground beneath your feet. Your senses constantly reinforce the idea that you are made of solid material. But when physics examines the structure of matter, the picture looks very different. The atoms that make up your body are mostly empty space. Inside each atom is a tiny nucleus containing nearly all the mass, surrounded by a vast region where electrons exist as quantum probability clouds. When trillions upon trillions of these atoms assemble together to form your body, they create structures that resist compression and movement through electromagnetic forces and quantum rules. That resistance is what your senses interpret as solidity. But underneath that familiar experience lies an astonishing reality. Most of the volume of your body is not filled with dense substance. It is mostly empty space structured by invisible forces. Now, saying that you are mostly nothing can sound misleading if we take it too literally. That empty space is not truly nothing in the philosophical sense. It is a region where electric fields exist, where electrons have probabilities of appearing, and where quantum laws determine how matter behaves. It is part of the structure that makes atoms possible. Still, the realization remains remarkable. The matter that forms you is not packed together like grains of sand in a jar. It is arranged more like a vast architecture of tiny nuclei and electron clouds interacting through fundamental forces. And this structure has a history that stretches far beyond your own lifetime. The atoms in your body were forged inside ancient stars billions of years ago. Through cosmic processes, those atoms eventually became part of planets, oceans, living organisms, and finally you. So what you call your body is not simply a solid object moving through the world. It is a temporary arrangement of atoms, mostly empty space, held together by the laws of physics and shaped by the history of the universe itself. By now, the picture of reality looks very different from the one our senses suggest. When you look at your hand, it appears to be a solid object with a clear boundary separating it from the world around it. But physics tells a deeper story. Your body is built from atoms. Those atoms contain tiny nuclei surrounded by vast regions where electrons exist as quantum probability clouds. The solidity you feel every day is not the result of matter being packed tightly together, but the result of invisible forces and quantum rules interacting between atoms. What you experience as touch, pressure, and resistance is really the effect of electromagnetic forces and the principles of quantum mechanics preventing matter from collapsing into itself. In other words, the familiar world of solid objects emerges from something much stranger beneath the surface. Your body is not a rigid block of substance. It is a dynamic structure made from atoms, fields, probabilities, and enormous regions of empty space. And this realization reveals one of the most fascinating lessons of physics. The universe is not built the way our intuition expects. The deeper we look into nature, the more surprising it becomes. As the physicist Richard Feynman once suggested, the universe is not only stranger than we imagine, it may be stranger than we are even capable of imagining. And what we have explored here is only a small glimpse of that deeper reality.